Hello everybody, this is Professor Iris Miano with your very first Day 1 lecture video for geometry, plane geometry. This is Math 32 for Santa Monica College. So the very first section that we're going to cover in this course will be section 2.1 on logic statements and quantifiers, as you can see on the screen. Accompanying this video, there is a PDF document on Canvas that I highly recommend that you print or somehow otherwise have access to it. Ideally, you would print it and write on top of it, filling out blank spaces and adding extra notes to the margins, circling things as we go, as you deem appropriate for retaining this material. And here we go. So if you have printed out the lecture notes as I recommend, the very first thing that you'll see is the term statement. We need to define this term so that we know very much clearly what a statement is. It's a particular type of sentence. There are other types of sentences that are not statements, and we're going to have a quick series of examples being able to distinguish between different types of sentences that are not statements, and then there's going to be one of them that is a statement. So what is a statement? It is a declarative sentence that is either true or false, but not both simultaneously. Okay, so here are 4 such sentences, and we're going to one at a time determine if they are statements or not. And if they are not statements, we're going to determine what type of categorization it has. And if it is a statement, we're going to also determine if it's true or false, because it can't be both, it's one or the other. Here is your first example. So we want to ask for each sentence, is the following sentence a statement? Would you like some water? Well, no, this is not a statement because it can neither be categorized as true or false. In fact, any sentence that has a question mark at the end is not a statement by definition. And so since we can categorize the sentence as a question, it is automatically not a statement. It can't be true or false. Would you like some water is not a sentence that can be responded to with a true or false designation. Okay? Here is your next sentence. Hand me that stapler. This sentence is known as a command, and anything that is asking something of another person or being is dedicated or categorized as such, and it cannot therefore be a statement, because you wouldn't say to the sentence, hand me that stapler, that it could be either true or false. I guess if you were handed a stapler after saying it, then you could say that it was true, but only after the fact and in regard to the subsequent action. So it has to stand alone as a sentence that is either true or false, but not both simultaneously. The next one is a little bit trickier. Here's the next sentence. Naive Melody by the Talking Heads is the greatest song ever written. Well, now, could that be attributed as true or false? Well, I guess so. Some people might say it's true. I personally would say that that's true. That's my favorite song. A little bit of personal info about me. But other folks might look at this sentence and be like, no, I think that's false. And so since there would be some warranted contention about whether or not this sentence is true or false, it cannot be categorized as a statement. In fact, it's considered to be an opinion. So opinions cannot be statements, which is something that I feel like a lot of folks these days confuse the two, whether statements could be opinions or not, and vice versa. All right, so here's our last example. 5 puppies is more than 3 puppies. This is a statement because it can be categorized as either true or false. In this case, it's true. 5 of anything is always going to be more than 3 of anything, and puppies just happens to be the unit in question, okay? So again, if a sentence can be categorized as either true or false, but not both simultaneously, or neither, then it is considered to be a statement by definition, okay? Great. Moving on. So in the next little bit, I want to introduce to you a series of statements that we would encounter, and they are going to have a symbolic form to them. They're going to have an English language form. Excuse me.
I didn't get that. Could you try again?
Oh gosh, Siri's talking to me. Please ignore that. Sorry about that, guys. That was so silly. So here is a table that, in fact, let me just go ahead and get the textbook open because I ganked it right from your textbook. So if we're talking about section 2.1, page 64, very early on in the section that we're covering here in this lecture, this table, 2.1, is a table of logic symbols. So in this section, we're going to be introducing several different types of statements. The following connectives are listed here in this middle, left of middle column. And they are going to take on the English language forms of not, and, or, the combination of if and then, and lastly, the phrasing if and only if. Here are the corresponding symbols associated with them. You have, for the connective not, a tilde in front of the symbolic form of the original statement component P. So P is just a symbolic placeholder for a phrase. Saying, we'll have lots of examples when we get to specifics, and it is known as, like, the categorization of this statement is a negation, okay? Furthermore, we have conjunctions, which take on the form of this little arched caret symbol, so to speak, between two statement components P and Q. The English language version of this connective is the word and. Similarly, for disjunctions, it is likened to the English language word or. And that symbol kind of looks like a V. It's really an upside down version of the conjunction symbol. But yes, it does look like a V. Then we will be discussing conditional statements, which have the if-then combination with statement components P and Q, which are the, excuse me, we're going to, sorry, I'm coughing into your ears there. We're going to categorize P and Q with specific designations a little bit later when we talk about conditional statements in more depth in a later section. And then lastly, we have the biconditional, which is like the conditional, only it goes in both directions, as you can see by the double arrow with the symbolic form, whereas the conditional has the arrow just only pointing in the, right direction. And we'll talk all about what that means in regard to its subsequent truth value when we talk about these last two. But for today, we're going to fully introduce the negation, the conjunction, and the disjunction statement types. Okay, cool. So here we go. Before we get too deep into that, and now I'm on page 2 of your lecture notes. So if you're following along with your lecture notes, you're going to want to turn the page. And so we could define truth value. And it's written on your lecture notes already, so you don't need to write this down, but I want you to definitely read it through all the way to yourself, and I'll read it out loud to you. Truth value is defined as being of a statement is true with a capital T if the statement is true, and false, capital F, if the statement is false. I know it's kind of a really basic, super obvious definition, but it's something we want to be able to establish very clearly before we get too deep into truth values. And they come about in regard to truth tables, which is our organizational mechanism by which we determine the truth value possibilities for a statement and its components. Okay, so let's bust out an example in which we fill out the truth table for the compound statement negation P, or not P, I guess you would say. So here is the basic setup for a truth table for a very simple one connective, one statement component truth table. So for however many statement components you have, now I'm talking about the letter P here, and for conjunctions and disjunctions, you're going to have two statement components that are connected via either conjunction or disjunction. We'll see that in a subsequent example. Now, if there's just one statement component possible, that means there's only two possible truth values for P, and that's the initial column that you fill out. You have one column with two possible outcomes, true and false. So I want you to, in the blank truth table for negation P, write a T and an F in the same positions on your lecture notes, okay? Now, these represent the two possible cases for the initial truth value of P alone, the statement component P. If you negate P, which is what we're going to be seeing as the truth value combination possibilities for the negation of P, you're just simply going to flip the true possible value for P to false if we're talking about the negation of P right there. Okay, so I want you to put a false under negation P in the row associated with the true truth value of the original statement P. Okay, or statement component P rather. All right, now you might guess from context clues at this point, if P is false, what would you suppose the truth value would be for the negation of P? Well, if you said true, you would be correct. You just give it the opposite truth value of the original statement component when you negate a statement component, okay? So hopefully everybody can follow that pretty clearly, but please let me know if you have any questions about this truth table that you've just filled out for the negation of P, okay? Now, we're going to move on to conjunctions and disjunctions. So, this is a statement connective using the word and, right, for conjunctions. And notice again the symbol here. It's kind of like a capital A, but without the horizontal little component there. And so what we're saying here with this item that I'm kind of underlining with my cursor is that we have P conjoined with Q. Another way to say it is P and Q. You could just replace the symbol with the word and. And the rule associated with conjunctions is that it is true if and only if both P and Q are true at the same time. Okay, this will become evident how the rule works if we fill out the truth table, which, you know, here it is. And there's a corresponding blank truth table already established on the middle left-hand side of page 2 on your lecture notes. Okay, so you're going to now learn how to fill out the two initial columns of your truth table. Here's the first initial column for P, the second initial column for Q, and then there's a third column here for the conjunction. Okay, so before you can figure out the truth value of the conjunction of these two statement components, P and Q, you first have to outline every single possibility of truth value combination for P and Q, and it'll be 4 rows this time. Now, why is it 4 rows when the negation of P, that first truth table that we filled out, was only 2 rows? Well, there's only one statement component for the negation of P. There's only P, right? P is the only thing involved, and it can either be true or false. When you have more than one statement component, you're going to have more than 2 possible outcomes, right? In fact, there's a rule, and it's 2 to the number of statement component power that's going to determine the number of rows that you're going to have to fill out for your initial statement component columns, right? So let's say, for the sake of argument, that there were 3 statement components in a compound statement that we had over here. Something more complex than just the conjunction. Just for the sake of argument, I wanted to establish the rule, okay? So let's say we had P, Q, and S statement components, and then there were connectives happening later on. you would need to initialize 3 columns, one for P, one for Q, one for S, and there would be 8 rows underneath that need to be filled out. And that's because you have 2 to the 3rd power number of possibilities there. Why 3rd power? Because in that case, there would be 3 statement components, P, Q, and S. Here, we just have P and Q. So we have 2 to the 2nd power, the 2nd power being associated with the 2 statement components, P and Q. All right, anyway, so I hope that's pretty straightforward, but we could talk about it more and have more examples in class if you so desire. Just let me know. Now, this is the initial way that you or the standard way rather, that you initialize those first 2 columns. And you got to do it this way every single time. It's a rule. It's a hard and fast rule, so that your remaining column that we're going to figure out the truth values for match up with my work, with the answers in the back of the book, with any other fellow students' work. We need to have a basis from which we start from that everybody's is the same. So it goes like this. Your first statement component always is TTFF, provided that you have 2 statement components total in your compound statement. Okay? So TTFF for Q and TFTF is going to be the truth value combination for the 2nd column. And notice that we have P and Q in this order as our headers for our initial columns as we read them from left to right. That's no mistake. We generally, as a rule, list the statement components in alphabetical order. So if the statement components happen to be like A conjoined with B, for instance, we would add A here, and it would be TTFF underneath, B here with TFTF underneath. Okay, the T's and the F's combination is always the same, and the column headers are always going to be in alphabetical order from left to right. Okay, so now that I've probably talked that to death, but please let me know if you have questions after that. We're going to fill out the conjunction truth value. And you're always going to be looking at the values of P and Q in each row to determine the value of the conjunction. Now remember, the rule is that P and Q is true if and only if both P and Q are true. Okay, so look at this first row. P is true, Q is true. So what'll be the value of the conjunction? It'll be true, right? Yeah, there we go. A little bit of a delay on the click. All right, look at the second row. T is true, but Q is false. They're not both true, right? So that means the conjunction has to be false there and false here because, again, one of them is not true. And if they're both false, what do you think? True or false? Well, it'll be false. They both have to be true at the same time. That's the only time the conjunction between 2 statement components will be true. In all other cases, it'll be false. Okay. Moving on to the disjunction, okay? That's going to be the separate V-like symbol. And the rule is that it is true if P is true, if Q is true, or if both P and Q are true at the same time. So here in green is another separate truth table that I've already initialized with the standard TTFF and TFTF for the P and Q columns. Go ahead and fill those into your truth table for this disjunction example if you haven't already done so. And please note, for the conjunction and disjunction on your lecture notes, there is a little space for you to write in your own vernacular what you perceive to be the rule. Or you can write it word for word as I presented it here and here. Okay, that's like the formal way to write out the rule. Okay, so let's go ahead and finish this truth table. Look at the first row. P is true, Q is true. So the disjunction between a true and a true is going to be true. The disjunction between a true and a false is going to be true. Because remember, the rule for a disjunction is only one of them has to be true. Either P is true or Q is true, or both are true at the same time. So here's both true at the same time. It's true. The P is true. That's good enough to be true. The Q is true for this third case. That's true. Only when both Q and P are false at the same time, that's the only time the disjunction is false. Okay, so a shorthand rule that I have to distinguish between conjunctions and disjunctions is to say, for a conjunction, for and, you got to have both true to be true. Otherwise, it's false. For a disjunction, you only need one true to be true. Okay, so anyway, if that's helpful for you as outlining the rule, by all means use that. Otherwise, come up with your own retelling of the rule. That's going to help you remember it. Okay, great. Moving on. Quantifiers and negation. Here we go. So we're going to introduce these universal and existential quantifiers. Okay. The first one that's defined, and it's already on your page here, so you don't need to write this down, but let's definitely talk about existential quantifiers. These are used as prefixes to assert the existence of something. So some examples of this are some, there exists, at least one, right? Okay, so these are terms that have this designation of, we're just saying that something is possible here, okay? Whereas universal quantifiers, on the other hand, are terms that are used to say all or nothing, right? Satisfies some condition. So none, no, all, every. These are universal quantifiers. They just kind of bring everything that is known within a certain realm to be either involved or uninvolved with a particular scenario, okay? Cool. So these particular quantifiers come up in logic in symbolic senses all over the place, and also, but we tend to use them in actual English language writing. And so I have this table 2.2 that's at the top of the next page that you see right here on the screen, and which I think is very helpful in being able to identify statements that have these particular kind of quantifiers. So you'll notice in this table 2.2 on page 68 that there are two universal quantifier statements, the first two rows here, and then we have some existential quantifier statements here on the last two. So you'll notice that if you move along to the other column in this chart, that the negation of a universal quantifier involves an existential one, and vice versa, okay? So we can use this chart in order to negate statements that have these types of quantifiers. So that's what I want to do in these next three examples, and then we'll be finished with this first section of material. Okay, so here we go. So reference this table, and let's together write negations for each of these three statements. The first statement being all turtles are purple. Now please don't get hung up on whether or not this statement is true or false. That's not the purpose of this exercise. The purpose of the exercise is just to simply write the negation of the quantified statement. Okay, so all turtles are purple. Now, which row in table 2.2 does that seem to match up with as far as the original statement is concerned? It seems to match up with the first row, right? All blank are blank. So go ahead and in the first blank put turtles, and the second blank put purple, and do the same thing in the negation, like later on in that row 1, column 2 area, and you should be able to come up with the negation of some turtles are not purple. You see how easy it is? Yeah, it can be that easy. Now, if your particular statement does not match up exactly with what's presented in this table 2.2, you might have to make a slight modification. And that's what I found to be the case with this next example. So the statement being, for part B here, at least one student received an A. See, I don't see this as being exactly like one of the given existential quantifier examples, but I found it to be like some, this phrasing at least one. I could rewrite it as, I got ahead of myself, the word some, in which it would read some student received an A. So if I did that, then I could match it up with, the last row of the table 2.2, some blank, and then I could negate it by no student received an A. You see what I mean? Where the blank would be student received an A, and you can literally transfer it from the sum, the last row of that table, and just put it onto the negation part of it and just say no student received an A. Lickety split. So again, there might be some instance in which you make a slight adjustment from another equivalent existential quantifier like we did here, going from at least one and saying, hey, that's equivalent to the word some, and then you can use the table from there. Okay, last example, some dogs are not friendly, right? I would say that is most like the third row in this table 2.2 where it says some blank are not blank, in which case I would negate it by saying all dogs are friendly. Okay, so if you think about the negation of these statements that contain quantifiers exercise as just fill in the blanks from one structure to another, it doesn't require more thinking than that. And believe it or not, this is what I would recommend that you do, at least in the initial endeavors of trying to tackle problems of this nature. And then as it becomes more and more comfortable for you, you can just kind of have a little bit more artistic license with it. But in your initial endeavors, I really recommend that you just stick very closely to the rules. And if you want to deviate from that, well, and if you have reservations as to whether or not it is equivalent, you could always run it by me, and I'd be happy to give it my seal of approval or not, or make adjustments with you. Okay, so that is a wrap. And so here is my reminder that there is for you that there is homework. So of course you'll want to read section 2.1 for yourself, however thoroughly you deem appropriate. You don't necessarily, in regard to reading a textbook, a math textbook in particular, you don't necessarily need to read every single word, but definitely go through all of the examples that are presented in the section. And then these are the problems that are listed in your syllabus as ones that I think you should practice. The next two sections that we're going to cover in the next lecture video will be sections 2.3 and 2.2 and 2.3. So you can look ahead if you want to be prepared for that. And then also we're going to have a quiz, a very short quiz in the next lecture. So by the next lecture, I mean day 2 class period. At the end of it, we'll have quiz 1, which is going to cover 2.1 material that we just went over in this video. Thank you so much for your attention, and I will see you again very soon in class.